Chapter 7 brings us to a discussion about something called the central limit theorem and how it deals with sampling distributions of data. First, some definitions for you. We're going to talk about population probability distribution, and that population probability distribution is the probability distribution of population data. So, in general, the probability distribution of a sample statistic would be called its sampling distribution. So what do we really know about the differences in population data and sample data? Well, the first thing you should remember is that the sample data doesn't include everything. Population data is everything. It includes the entire population that you're studying, whereas sample data is just a selection of that population. Hopefully a representative selection, but still, it's not going to have everything in it. So there are going to be some errors that are going to occur in your data. A sampling error is just that. It's a statistical error that occurs when a sample does not represent the entire population. Now, it's caused by using a sample instead of the entire population to calculate, for example, the mean. When we calculate the sampling error, we do it by subtracting the population parameter from the sample parameter. So if you wanted to look at the sampling error of some data that you had collected, you would take the mean or the average of the data that you collected of the sample. And from that sample mean, you would subtract what you know to be the population mean. Now, we're assuming, of course, that the sample is random and that no other, what we call non-sampling errors have been made, but this would be called our sampling error. Sampling errors are basically unavoidable. These are the errors that happen simply because we are dealing with sample data instead of population data. So what do we mean by non-sampling errors then? Well, this is the term used in statistics, and it talks about errors that occur during data collection that causes the data to differ from the true values. Now, these errors generally are avoidable. They're either random, they might be random, they might also be systematic errors, and they can be challenging to spot if you're doing a survey or a sample, or even if you're taking a census. Systematic non-sampling errors are actually worse than random non-sampling errors because these result from the survey or the census having to actually be scrapped and you can't use it anymore. The higher the number of errors we find, the less reliable the information that has been gathered in our survey. And when non-sampling errors occur, there's a rate of bias in the study or survey that actually goes up. Now, if a sample is non-random, and hence this is the most likely non-representation, the sample results may be too different from the actual census results or the population results. The questions may be phrased in a way on our survey that are not fully understood by members that are taking the survey, and this would cause a non-sampling error. If they didn't understand how they were supposed to answer, they would not be giving the answers that would be accurate. There's another problem with taking surveys and getting information from people, and it is that respondents have a tendency sometimes to give false information, especially if you're asking information that's sensitive to them. For example, if you were asking about past history of drug abuse, some surveyors would be tempted to not disclose that information, even if they were ensured that the survey was anonymous and that they wouldn't be identified. There's also the problem that the poll taker or the person that's taking the survey might make a mistake. It might enter a wrong number or might make an error when entering data into the computer. Well, this would be an actual non-sampling error. As you can see, most of these errors, if we do a really good job on our survey, non-sampling errors should be avoidable, whereas sampling errors simply are not. So let's talk about how we calculate a sampling error. Like I told you, these are the errors that are going to happen just because you have sample data instead of population data. So basically, it's going to be the difference you have in sample and population data. So for this example, we're talking about a statistics class. It's an advanced class. There are only 10 students in it. And I've listed the midterm scores in this chart. Now, suppose we take a sample of 6 scores from this population of 10, and this sample includes the scores 70, 75, 80, 80, 90, and 95. we're asked to take that sample and find the sampling error. To find the sampling error, you're going to need to calculate the mean of the sample, and you'll also need to calculate the mean of the population. You have the mean of the population here. It's the 10 scores. So you'll add these 10 scores together. Notice that some of these scores occur, frequency is more than 1, so you'll have to add those in more than one time. So you'll calculate the mean of the population, the 10 scores, and then calculate the mean of the sample, just the 7 scores that you're given. So here's your solution. The mean, the population mean, notice the symbol that's being used, is adding all the 10 scores together and dividing by 10, comes out to be 79. But if we just take the 7 scores in the sample, we would take those scores, the 6 scores in the sample, we would take them and divide by 6, and we would come out with 81.67. Well, that's different from the population mean, isn't it? And it's due to the fact that we didn't add all of the scores, we just were dealing with our sample. So how do we get a sampling error? Well, you always take the sample mean, and subtract the population from it. If you do it in reverse, you'll get a wrong answer. So let's take the sample mean of 81.67 and subtract the population mean of 79, and we have a difference of 2.67. Now, why did this occur? Why did we have this difference in the two means? Just because we only picked a selection of the data, we didn't add all of the scores. So a sampling error is just that. It is unavoidable. It is due to the fact that we take a sample of the data instead of having all of the data. Now, as we know, it's very difficult to get population data, so quite often what we're dealing with is the sample data. All we have is sample data, so it's necessary for us to understand or figure out a way that we can calculate probabilities using just a sample of the data. Now, we have to also be able to calculate the mean and the standard deviation of what we call the sample mean. Now, sample mean is always written with a bar above the x, so we'll talk about the mean of the sample mean as being the mean of x bar, and the standard deviation of the sampling distribution as being the standard deviation of x bar. Now, this is really the calculations that we do to adjust for having sample means instead of the population mean to deal with are not too complicated. One thing you can remember is that the mean is not going to change. For our purposes, the mean of the sampling distribution of sample means, which is that mean of x bar, is always going to be equal to the population mean. So the mean is the mean is the mean. It's not changing on us. The standard deviation of the sampling distribution of x bar, or of sample means, is going to have to be adjusted. We're going to take that population standard deviation that we've been dealing with, and we're going to divide it by the square root of our sample size. So let's take an exercise and work a few of these just to make sure you know how to do this. It's a simple calculation. Let's say that we have 600,000 postal workers in the U.S., and the mean wage for all of them is $25.57. So it has a standard deviation of 0.05. Now that's going to be the population standard deviation. How do I know that? I know that because it says the mean wage for all and the standard deviation with a standard deviation. So it's talking about population there when it lists those. So we want to find the mean and standard deviation of x bar for a sample size of 400, and then for 95, and then for 600. So we're going to do all three of those on page 3. So let's look on page 3 together, and we'll take the first one that has a sample size of 400. Now, the population size is not going to change for our problems. It's always going to be the same 600,000. The population mean is also going to be the same. It's 2557. And the population standard deviation is going to be the same. You could go ahead and fill that in for A, B, and C if you wanted to. Now, there's a question here that we're asked. We're asked to check and see if n, sample size, divided by n, population size, is less than 0.05. Now, this is the condition that allows us to use these two formulas for calculating the mean of x bar and the standard deviation of x bar. So it's a real simple check that you need to be familiar with, but we probably won't do it very much. That you might be asked a question about it on a test, but you probably won't be asked to carry this out. Let's take our sample size of 400 and divide by our population size of 600,000, and we come up with the number 0.0006. Is it less than 0.05? Yes, so we're allowed to continue. So now, what exactly is the mean of x bar, the mean of the sampling distribution of sample means? That's what that is, but I'm going to call it the mean of x bar. Well, it's the same as the population mean. For our purposes, remember, we're not changing the mean. It's always going to be the same, okay? So that's easy. What about the standard deviation? Well, from now on, with standard deviations, in samples, you're going to have to make an adjustment. You're going to take the standard deviation of the population, and divide it by the square root of the sample size. In this case, the square root of 400. When we do that, we find that it does change. Instead of 0.05 in our calculations, we're going to use 0.0025, and that's really the biggest difference. If you want to put a star by it, that's the biggest difference that you're going to have to face when you're dealing with sampling mean data instead of just plain x values, data values like we did in chapter 6. All right, go ahead and stop your tape now and go ahead and complete part B and part C, and then you can start back and check your work. Right, on the second part of this, it said, what's the population size? And remember, I told you, for this problem, population size, population mean, and population standard deviation don't change. We do have a difference here, though. We're going to take, this time, 95 and divide it by 600,000. And we're going to come up with 0.0001, which is less than 0.05. So our calculations are okay for what we're using for the standard deviation of the sampling distribution of sample means and the mean. Next, I'm going to say, what is my mean of x bar going to be? Well, I'm going to use the same number that I used for population mean. Standard deviation, that calculation will take the population standard deviation divided by the square root of my 95, which is my sample size. So this comes out to be 0.0051 this time. When I do 600, once again, I'm not changing my population data. I'm not changing any of the population data, which really, if you're using the same scenario, really never changes. I do have to adjust because I have a new sample size here. So I'll take that 600 this time and divide it by the population size of the population, which is 600,000. And this time I come up with 0.001. Is that less than 0.05? It is. Population mean stays the same. And here's my calculation. Population standard deviation. This time I'm dividing it by the square root of 600. And I come up with 0.0020. So what have you learned from this? Well, when we're dealing with sampling data, we have to adjust the standard deviation of sample means that we're going to use. So we will have to divide by the square root of the sample size before we can do some of our other calculations. So let's talk a little bit about this sampling distribution of sample means, sampling distribution of x bar. The shape of this distribution will be considered a normal shape, normally distributed, if one of the following two conditions is true. The first condition, the population from which samples are drawn, is normally distributed. So if I'm pulling from a normal distribution, a normal population distribution, then it is assumed that my sampling distribution of sample means is also going to be normally distributed. The second condition is, if I have a large enough sample size, then it's considered I will have a normalized sampling distribution also. Now, according to the central limit theorem, for a large sample size, the sampling distribution of x bar will be approximately normal regardless of the shape of the population distribution. In other words, my population distribution could be skewed, And if I have a sample size of 30 or greater, which doesn't seem too big to us, but that's considered large enough according to central limit theorem. If I have a sample size of at least 30, then I can say that my sampling distribution is going to be normally distributed, even if the population distribution was skewed. So let's look at what this looks like visually. These are examples of samples that were pulled from populations or from data that was skewed, and you'll see if we have a smaller sample size, as you can see in this lower one, the gold colored bar or gold colored curve, we have a skewed distribution. It has a right skew to it. But the larger that we pull, this, in other words, if I pull 10 samples, for example, it's bringing the data closer and closer to what the actual mean is. It's bringing it back toward the center of the curve. And by the time I've pulled 100 samples, I basically have a normally distributed sample distribution. And that's what I want. Why do I care? Well, because I want to find probabilities. And I want to be able to standardize this data to z-scores and use the normal distribution tables to find probabilities regardless of its shape or the characteristics of the underlying distribution. That's what's important to me. So I need to be able to determine if I can normalize this to the z-table, and I can if I either, number one, come from a normal population when I pull my sample, or number two, if I have a large enough sample size, which is 30 or more. So just to reiterate what I've just said with an actual practical exercise, let's look at the bottom of page 4. It says the mean rent paid by all tenants in a small city is $15.50. There's a standard deviation of $2.25. Now that said the word all, didn't it? Which meant that this is a population mean, population standard deviation I'm dealing with. However, this population distribution of rents for all the tenants is skewed to the right. So I don't have a normalized data set. I've got a skewed data set, a skewed population. They want us to calculate the mean and standard deviation of sample means and describe the shape of the sampling distribution if I have a sample size of 30. Well, if I have a sample size of at least 30, then it doesn't matter that my population was skewed. I can say my sampling distribution is normal. That's the shape of it. So I can go down to both of them and say, well, this one has a sample size of 100. So I have a normal population distribution. That was the for the sampling distribution. Now, what's the mean? Well, the mean doesn't change. Remember that? So the mean I'm going to pick up is going to be the 1550 for both of them. The mean of the population is going to be used for the mean of the sampling distribution of sample means. And then I need to do this adjustment for the standard deviation. I need to take the population standard deviation and divide it by the square root of my sample size, which in this case was 30. I end up with 41.0792. 4 decimal places is always enough. And then I'll end up with this one if I take that population standard deviation and divide it by the square root of 100, which is dividing it by 10, isn't it? I end up with 22.5. Now, let's just remember, how do we calculate the z-value? Well, now we're dealing with the z-value of the sample mean. So we've made a little bit of an adjustment. This time, instead of using x minus the mean, the data item minus mean, we're going to use what we call the sample mean. The sample mean is going to be very much like the same thing. It's going to be the sample mean that we're interested in, okay? And we'll subtract the population mean. And this time, then we will divide, and this is where you need to pay attention, we'll divide by the standard deviation of x bar. In other words, that's the standard deviation we adjusted. I put down the formula that we had in Chapter 6 for population data only, and so that you can see the difference in the two. So let's take a look on page 5 at this example. We have a population that has a mean of 285 and a standard deviation of 71. We draw a sample size of 50, so really it doesn't matter whether that population was normally distributed or not, does it? We've got a big enough sample size to take care of it. And we want to know what the probability is that the mean of the sample, in other words, the sample mean, is going to be less than 279. So first, let's take a look and see what we can identify out of the problem. Sample size of 50 means that our little n is equal to 50. And then the mean of the population is also the mean of x bar. I just wrote those together so you would see it. So we're going to deal with that 285 being our mean. And next we're asked the standard deviation of the population. Well, you were given the standard deviation of the, standard deviation of the population up here, so that is 71. Now let's do our calculation for the standard deviation of x bar. Let's take 71 and divide it by the square root of our sample size, which is 50, and come up with, and we'll use 4 decimal places for almost all of these standard deviations until we get to chapter 9, I believe. We'll say it is 10.0409. Okay, now let's kind of check this out. I've given you a curve down here at the bottom so that you can actually draw your curve and put your information there. So let's do that. Let's go ahead and you can label the curve at any point, but I'm going to do it now. I know I'm going to use the z-table because they've asked me about probability. So that's the only way I have right now to find probability. But instead of x values, this time I'm dealing with sample means. So I'll put x bar down there. So what's the sample mean? Well, the mean, remember, is the mean is the mean. It's not changing. So the mean of this data set is going to be 285. I'm going to go ahead and set that up. The sample mean I'm interested in is right here. What's the probability that the mean of the sample will be less than, and they asked me for less than 279. Well, 279 falls to the left of my mean, population mean, and so I'm going to put down 279 here, and I don't know z, and I'm going to shade the area to the left, less than. I know when I find that z-score, I can look up this area and it will give me the probability. So that's very familiar. I haven't changed much on you. All I've changed is that you have to recognize that you're dealing with sampling data and you have to do the division for the standard deviation. So let's see what we can do here. Let's convert and see if we can actually get our z-score. We use the new formula and we say the sample mean that we're interested in, well, that's 279, subtracting that population mean of 285, and we'll divide by that new standard deviation, the one we calculated, 10.0409, which is really pretty much all I'm changing on you at this point. I come up with negative 0.598. Well, I'll call that, I'm going to say that's going to be really close to negative 0.60 since my z-table has 2 decimal places. And then I go to the z-table and I look up the area to the left. So I'm on the z-table, I want negative 0.60, and here it is, 0.2743. So this area is 0.2743. And what that means to me is that the probability that the sample mean that I select from this data that will be less than 279, which is the question I was asked, right, is the same as the probability that z will be less than that z-score I calculated. And that probability is 0.2743. Or if I'm asked to write it as a percentage, I would say 27.43%. You have to watch to see what you're asked to give, what format you're asked to give the answer in. Okay, so let's do a few of these. I'm going to look at this example with you, this exercise on page 6. It says Uni's a personnel manager in a large corporation, and every month she has to review 16 employees. From past experience, she has found the reviews take her approximately 4 hours each, and there's a population standard deviation of 1.2 hours. Okay, so what we're saying is we're going to say from past experience, she has a mean, we'll call that her population mean of 4 hours, and a population standard deviation of 1.2. Now, x is going to be the random variable representing the time it takes her to complete one review, and assume x is normally distributed. Now, X bar is the random variable representing the mean time to complete the 16 reviews. In other words, it's a sample mean that we're looking at. The sample of 3 reviews is chosen. Well, 3 reviews is definitely not 30, but we're assuming that this population is normally distributed, so we're okay to use the z-table. Find the probability that the mean of this randomly selected sample will be, and it gave us 2 numbers from 3.5 to 4.5. So let's write down what we know. What is n? Well, there's our sample size. Small, there's only 3 reviews chosen. What's that mean? Well, the mean is what she has found the reviews to approximately take. So we'll say 4 hours for our mean, and a standard deviation of 1.2. That's, and we were even told population standard deviation. We need to do the adjustment because it's a sample that we're dealing with. So we'll take the 1.2 and divide it by the square root of 3. That gives us 0.6928. Now, we need to find the sample mean between 2 values, right? Between 3.5 was the question, and 4.25. She wants to know what's the probability that it's going to take between 3.5 and 4.5 to complete. So we'll have to come up with 2 z-scores. Let's go down here and put it on our chart. I know I'm dealing with z. I also know I'm dealing with sample means. I can put my mean, my population mean, in center because I use it for both, and then I can place the 2 numbers I'm interested in. And they go 1 on each side, don't they? So this one is 3.5. I don't know the z-score. And this one over here is going to be 4.25. Once again, I don't know the z-score. And I want this area that's between the 2. So I know I'm going to find the z's, look up the areas to the left, and because I'm between 2 z-scores, I'll be subtracting those to get the area in between, just like we did before. So I need to do the calculations for z. First z-score is going to be, I'll use this first one, 3.5 minus the center mean of 4 divided by that standard deviation that I calculated. And I come up with a z-score of negative 0.72. Next, I'll calculate the second one. I'm going to start with 4.25. That's my sample mean, and I'm going to subtract the mean, the population mean of 4, divide by the standard deviation that I calculated, and I'll come up this time with a z-score of 0.36. Be sure you're doing the math of these and not just trusting me to do all of your math for you, because you'll be lost when you come to a test. Okay, so let's write our probability statement using both sample mean and z-scores just so that you know what we're dealing with. The probability that the sample mean will be between the 2 numbers we were asked about, 3.5 and 4.25, is the same as the probability that the z-score will be between the 2 z-scores we found, negative 0.72 and 0.36. What is that probability? Well, first we got to look up these 2 z-scores. Let's go to the negative side and look up negative 0.72, and we find it to be 0.2358. And let's go to the positive side and look up 0.36. 0.36 looks like 0.6406. So I take those 2 and I go 0.6406 minus 0.2358, and I come up with the area between the 2 z-scores. 0.4048 is what I get, and that would be the answer, or I could write it as a percentage. It would be 40.48%. In other words, there's a 40.48% probability that doing her reviews will take between 3.5 and 4.25 hours. Now, you have an exercise to do on your own at the bottom of page 6, and it talks about credit card balances that are normally distributed, a mean of 2870, a standard deviation of 900. So that's a population mean and a population standard deviation. Now, I've given you two problems using this data, but I want you to note that one of them is dealing with population data like we did in Chapter 6. The other one is dealing with sample data like we have just done in Chapter 7. I put these together for you so that you can see the answer, so that you can see the difference in the way they're worked, and so that you can see the answers and check yourself. Try those and see how you do. Now the next section that we're going to be dealing with, and we're starting this on page 7, is really proportion data. Now proportion problems are not something that we've talked about in the past, but they're not too different, or we're not going to work them too differently than we do the population data and the sample mean problems. The only thing you need to be aware of is there's new definitions, and we have to be looking for the proportion data, which is lots of percentages, lots of decimals. So what is the population proportion? Well, we call that P, and it is defined as the percent of the population that has a certain characteristic, the characteristic that we're interested in. Now the sample proportion, p hat, is the percent of the sample that has the characteristic we're interested in. So we're going to be talking about, instead of x's and x bars, we're going to be dealing with p's and p hats. And those are going to be really what we used as the mean and the sample mean. The p and the p hat are going to kind of take those places. So when we calculate, or when we do calculations for population and sample proportions, it's not really hard. You should be familiar with it already. For the population proportion, we take X, that's the number in the population that have the characteristic, capital X, and we would divide that by the total number in the population. So for instance, if I was interested in how many people had red hair at IRSC, I would count the number of redheads, that would be my capital letter X, and I would divide by the total number of people at IRSC, that would be my capital N, and that would give me the proportion of redheaded people at IRSC. You do the same thing when you're dealing with a sample, except this time I'm dealing with a sample that I took, looking for perhaps redheaded students in a statistics class, or how many out of the sample, and I use my statistics class as a sample. Now, understandably, that's a bad representation of the whole population, but if I did that and had a smaller percentage, or I had a smaller number, I would look for the number of redheaded people in that sample and divide it by the total number in the sample, and it would give me a decimal, and the decimal is basically the proportion. Now let's kind of look at what we're dealing with the mean, or the population proportion, so to speak, and the sample proportion p hat. If we take a lot of samples, repeated samples of a certain size from a population, and we're looking for a certain category of interest, and we find out that we know the population proportion is P, then we say the mean of all the sample proportions is basically the population proportion. Now, what I'm really trying to say is that you don't have to worry about that mean of P hat, or the mean of the sampling proportion. You're going to use the population proportion for that. The probability distribution of that sample proportion p hat, we would call that its sampling distribution, just like we did with x and x bar when we were talking about the sampling distribution. So just to reiterate and put it for you plainly, the mean of the sample proportion p hat, we call that the mean of p hat, and then it is equal to the population proportion. So you're not going to have to do too much with calculations of that unless they give you the number that has the characteristic in the population and the number in the population. You'll have to do the division to find the population proportion. The standard deviation, however, is calculated with a different formula than we are used to using. This time we take p times q and divide it by n, and then take the square root to get the standard deviation of p hat. Now, how do you find P and Q? Well, you've got to be given P, the population proportion, and Q, of course, is just equal to 1 minus P, and of course, N is the sample size, so it's really simple for us to do this calculation. It's important to note that sampling proportions, the sample size has to be much larger for proportion problems, so we have a check that it's necessary that you know, and it is this one. Both the sample size times the population proportion P and the sample size times Q must be greater than 5. If that's true, then you know that your sample size is sufficient for you to use these formulas that we're going to use for the proportion data. Now your calculation for Z is fairly straightforward. This time it is P hat, which would be the sample proportion we're interested in, minus P, which is the population proportion, divided by that standard deviation of P hat that we calculated using the square root of P times Q divided by N. So let's take a look at this example on the top of page 8 on page 8. It says, according to a Gallup poll, 62% of Americans identify as middle or upper class. Now, they've said 62% of Americans. That's really all Americans. They didn't really say it, but it is. And so they have identified the population proportion for us. That's P is 62% or 0.62. So I can go ahead and write that down as soon as I find it. P is equal to 0.62. Next, they say they want to let P hat be the proportion of a random sample who identify as middle or upper class. And they want us to find the mean and standard deviation of the sampling distribution of P hat for the samples that are 36 and 75. Well, the mean is the same as the population proportion, so that's not changing. You can say P is going to equal the mean of the sampling proportion also, or P, and so we would just write it down, 0.62. We don't have to do too much for either one of those. And the standard deviation does have to be calculated, and it changes based on sample size. So we're going to come up here and we're going to say that is the square root of P times Q divided by N. Well, I know P, that's 0.62. But what is Q? Well, if P is 0.62, Q is 1 minus P, or 0.38. So I'm going to multiply 0.62 times 0.38 divided by my 36. All of that is under the radical sign. And for proportion standard deviations, I'm going to suggest you take them to at least 6 decimal places, because proportions have lots of decimals in them and you need all the precision you can get. So I came up with 0.080898. Let's do the same thing. Only thing we're changing is the sample size. So I've got the same population proportion, or P. I've got the same value for Q, but I'm going to divide by 75 this time. Once again, all under the radical. And I get 0.056048. Now, be sure you try this with your calculator so that you'll know how your calculator works doing these square roots. Now let's take a problem. I've got a sample of 75 Americans. That's going to be N, isn't it? And I've even written it for you. N is equal to 75. They're over 25 years old. It's randomly drawn. I want the probability that less than 76% identifies middle or upper class. Now, I'm going to check and see if my sample size is big enough. I didn't do this before, but I have to make sure that N times P and N times Q are both greater than 5. N times P is going to be 75, which is my sample size, times P, which is 0.62, and I come up with 46.5. Well, that's definitely bigger than 5. Over here, N times Q is 75 times 0.38. Well, in this one I got 28.5, so it's definitely bigger than 5. That's just to ensure that our sample sizes are large enough. Proportion problems need bigger sample sizes, and so this is the check to see if the sample size is large enough. Now we're asked to find the probability that less than 76%. P hat is less than 0.76, so I've got that written down for me. I know my mean of P hat has to be the same as my population proportion, so it's 0.62. And I'm going to calculate the standard deviation with this sample size of 75, but I've already done it. Here it is, isn't it? So it's going to be the same thing here. It's going to be the square root of 0.62 times 0.38 divided by 75, all of that under the radical, and I already did it, so I'll just copy it down here. Okay, I'm ready to go. I need to calculate my z-score now. Now, these problems are very much like what we've done for the data items, the x-values, and the sample means, the x-bars. The only difference is we're dealing with proportion data. So how do I calculate the z-score? Well, remember the formula. We're going to say it's pretty similar to what you've been doing. I'm going to accept a lot of decimals, right? So I'm going to use my 0.76 here, my sample mean. I do want to put this on my graph before I get going. And instead of using sample means or x values, I'm going to use p hat. That identifies what type of data I'm dealing with. And there's my population proportion put down there in the center. Okay, so what am I interested in? I'm interested in less than 0.76, right? So p hat less than 0.76. I'm going to find 0.76. I don't know z, but I want this area less than. It'll be easy because when I find that z-score, I'll just look it up. So I start out and calculate z. I take 0.76, I subtract the center, 0.62, I divide by the standard deviation I calculated, and I come up with a z-score of 2.497. I'm going to go 2.50 with that one, okay? I'm going to say it's about 2.50. So this is what I'll put down. And so the probability that that proportion, the sample proportion, is less than the 0.76, which is what I was asked, is the same as the probability that z is less than 2.5. And I can look that up on the positive side of my z table, can't I? 2.5, here it is, 0.9938. So that answer is going to be 0.9938. If I wanted to look at it as if I was asked about the percentage, it would be 99.38% probability. Now, you need to work the problems on page 9 completely and then check back with me and check your answers. And there's not really too much difference in these and what the problems we've been working before with the population data and the sample data, where we're looking for probabilities and we're using the z-table. The major difference with proportion data is the standard deviation. For both of the other types of problems we've been dealing with, we've been given a population standard deviation. Well, not so for proportion problems. And quite often I have students email me and say, I can't do this problem. They didn't give me a standard deviation. How am I supposed to do it? Well, remember, proportion problems, you have to use P and Q and N to calculate the standard deviation. So it quite often doesn't look like the same type of problem at all. So I want you to try the ones on page 9 and then come back to me and see if you can check your work. Let's look at the first exercise. It says, according to a recent research by a communications firm, 56% of people worldwide believe that capitalism as it exists today does more harm than good in the world. Now that's 56% of people worldwide. I would say that is my population proportion, okay? I'm just going to put it down there and say that's got to be it. Next, let p hat be the proportion of people in a random sample who believe that capitalism as it exists today does more harm than good in the world. In other words, they're wanting us to compare the same thing. That's good. We have the population proportion right. Now, let's suppose a random sample of 100 is selected, and we want to know what's the probability that more than 59% of the sample believe that capitalism does more harm than good. They've given us all we really need to know. Let's start filling in some of the information. And these are the things you need to say, okay, it's a proportion problem. I need N, I need P, I need Q, and I need the standard deviation of p hat to get me started. All right? So let's write those things down. What was my sample size? Well, there were 100 people. What is my population proportion? 56%. I'll write it as a decimal. And what's Q then? Well, it's going to be 1 minus 0.56. So that's going to be 0.44. And what's that standard deviation? I calculate from the square root of P times Q, and I divide that by N, and all of this is under that radical sign. So I come up with 0.049639. Now I'm ready to get started. Let's draw the curve and label it as a proportion problem with p hat down here. And let's put our population proportion in the middle. We're ready to go. What did they ask? They want to know the probability that more than 59% believe that capitalism as it exists today does more harm than good. In other words, they want to know the probability that the sample proportion is greater than 0.59. Now, you're going to have to start writing these statements for yourself. That's why I did it for you. And then I'm going to go further and say, okay, that's the same as the probability that z is greater than a certain number. I don't know the z yet, right? And that will be, and I'll put it out there so I can put my answer. So where does 0.59 go? Well, 0.56 is in the center, 0.59 is over here. 0.59 would be here. I don't know the z-score. I'll have to calculate it. Greater than is to the right, isn't it? So great. I'm going to have to look up the area to the left, and then I'm going to have to calculate the area to the right. All right. How do I calculate my z-score? Well, for the z-score, I say it's equal to p hat. That's the one I'm interested in, the 0.59, minus the p in the center, the population number in the center, and divided by, well, the standard deviation that I had to calculate. And I get 0.60 or 0.6. Oh, looks really close to that population and that proportion, doesn't it? But it's not. It's a z-score. So I can look up the area to the left, and I will. I'll go to 0.6, and I'll see, okay, it is 0.7257. 0.7257. And I know to get the area to the right, I have to go 1 minus 0.7257. And when I do that, I'll come up with that area to the right. Now, I did the calculation, but I want to show you the shortcut. Since it's an area to the right question, I could have looked it up instead of looking up the positive 0.6. I could have looked up the negative 0.6, and it would have given me this number exactly. I wouldn't have had to subtract from 1. Let's look it up. Negative 0.6 is right here. That is 0.2743, which is exactly what I came up with, and you can do that if you understand it, okay? So that number, 0.2743, would also be, as a percentage, 27.43%. That's the probability that more than 59% believe that capitalism does more harm than good. Now they have another question, same data, but they want to know what's the probability that less than 33%. So what have they changed on you? The only thing they've really changed is the probability question. This time, it's the probability that p hat is less than 0.33, isn't it? Okay, that's going to be the same as the probability that a z-score is less than some number that we'll have to calculate, and we can figure this out. Let's go ahead. It's the same data. So certain things on our curve are going to be exactly the same, and the mean is one of them. The population proportion is one of them, isn't it? Let's see if I can get this up here so you can see it. Okay, so where is 0.33? Well, it's over here somewhere. And we want the area to the left of that. We want less than. We've got to figure out our z-score, but when we find it, all we have to do is look it up, and it'll tell us what we want to know. So let's calculate z. We've already calculated the standard deviation we need, so we really don't have to do too much with this one except for a new z calculation. I'm going to say 0.33, the sample proportion that I'm interested in, minus the population proportion of 0.56, and divide by the 0.049639. Look at all the decimals. Proportion data has so many more decimals than other data. Okay, so I come up with a negative number, a negative 4.63. Wow, that's off the chart over here, isn't it? So I drew it in the wrong place. I'm kind of going to move it over. I'm going to say this is not where that line goes. That line would go over here, wouldn't it? And it would be a z-score of negative 4.63. Well, what's past? I can't look it up. It's not on my chart. What is past? What is smaller than a negative 4.63? It's not on my chart. Nothing's out there. So that probability is 0. All right, let's try number 3. There's a random sample. This time, 300 people are selected. What's the probability that between 140 and 185 hold this opinion? Now, this is really dealing with the same data, but they did change the sample size on me, didn't they? So, let's see what I know. I'm going to say a random sample. So they've changed quite a few things on this problem for us. I'm going to rewrite my information just so I have it all together down here. I've got N this time is 300. Now, they didn't change the population proportion, so I can say that's still the same, 0.56. And that means Q is also the same, 0.44. But because I have a new sample size, I have a new standard deviation, don't I? Standard deviation of p hat. This time, I've got to do it again, 0.56 times 0.44. This time divided by that new sample size of 300. And I come up 0.028659. Okay, so I'm kind of ready to go. And then it says, I want my probability statement. What's the probability that between 140 and 185 people hold this opinion? Now, that's a problem because they didn't give me the proportion of people that hold the opinion, but they did give me the numbers to calculate it. So what would I do? Well, I have to say, what's the proportion of 140 out of 300, right? Well, 140 out of 300 is a simple division problem, and I can come up with a proportion there, 0.47. So that's the 140. And then I say 185 of the people would be 185 out of the 300, and that would give me 0.62. So here's my statement. I want to know the probability that p hat is between 0.47 and 0.62. How did I find it? Well, I took the number of people that they said they were interested in, 140 people out of 300, simple division, and 185 people out of 300, and I came up with the decimal equivalency, so those are proportions. So it looks like I got to have two z-scores, doesn't it? Probability that z is between two numbers also, and then I can come up with my answer. I'm running out of room, but I think I can do it. Let's draw it, put it on the curve. I've got z, and I've got p hat, and I've got the same population data here. So that's set. Now I want to go 0.47 and 0.62. Well, 0.47 is over here. I don't know z. And 0.62 is over here somewhere. Again, I don't know z, but I know I want the area between them. I'll find the two z-scores, look them up, and subtract their areas to get that area in between. Let's calculate the z's. The first z-score is going to be 0.47 minus 0.56 divided by that new standard deviation, the one I had to calculate because I have a new sample size. So that comes out to be negative 3.14, I believe. You're going to check my work, okay? Make sure I've got it. Negative 3.14. And the second z-score comes out to be 0.62 minus 0.56, dividing it by the new standard deviation. And I come up with 2.09. Okay, that's easy enough. Let's look them up. I've got the positive table here. Let's go ahead and look up positive 2.09 real quick. 2.0, and I go all the way across to 9. Can you see it? It's going to be 0.9817. Okay, this area, 0.9817. Now this one, dealing with negative 3.14, got to go to this table, this side. Negative 3.1, I'm going to go all the way over to 4, and I find 0.0008. So a very small area that I'm subtracting. I'll come over here and do that. 0.9817 minus 0.0008 Looks like that's going to be a 9, 0. There it is. Okay, the area between 0.98, 0.9. I didn't finish filling this in, but the area between 0.9809 or 98.09%. That one was a little bit tricky because you did have to calculate the proportions, and you might be asked to do that. Now, I just want to look at one more thing with you because you might be asked to find a sample size. You know, I need to know how big a sample do I need to use if certain things happen. And I want you to note that you have a formula that uses the sample size n, and it's this one. The standard deviation of x bar is equal to the standard deviation of the population divided by the square root of the sample size, right? So what if you know everything about this data that you're working? What if you know the standard deviation of the population, and what if you know the standard deviation of the sampling distribution that you're interested in? Could you solve for n? Well, it's really simple, but it's something that we might have to remember how to do. So I'm going to fill in 60 for the standard deviation of x bar, and I was given 1200 for that standard deviation of the population, and then I'm still solving for the square root of n. So just so you'll remember how to do this, because for some of us algebra has been a course we took recently. What do I do first when I have an equation that has fractions is I multiply both sides by that common denominator. So I'm really going to multiply this side by the square root of n, and I'm going to multiply this side times the square root of n. And what that's going to do is it's going to cross reduce over here and get rid of my denominators. And I'll really have 60 times the square root of n is equal to, and all I'll have over here is 1200. It's getting simpler, isn't it? Now I want that n to be all by itself, so I'm going to divide this by 60, so those will cross out. Well, I have to do the same thing to the other side, and when I do that, I see, well, all I've got over here is 20, right? So square root of n here is equal to 120 divided by 6, which is 20. Now, how do I have the square root of n, and I want just n. Well, then I have to do something. I have to square it, don't I? If I square that side, I have to square this side. So now I'll have n is equal to 20 times 20, or 400. So my sample size would need to be 400. If I was given the other two pieces of a three-part equation, an equation that has three unknowns, if I have two of them, I can always solve for the other one. And that's something you might be asked to do. So just to kind of get familiar with that process again. Right, this completes Chapter 7. You should be able to complete your work in the homework and quizzes now and start getting ready for testing.